Hello, everybody. Today, we are going to see the first part of factors affecting the nucleophilic substitution reaction. So, let us go to the factors which affect the nucleophilic substitution reaction. I am Dr. Urmila Joshi, and given here is my mail ID. You can contact me on mail if you have some difficulty regarding the lecture. So let us try to understand the factors which affect the nucleophilic substitution reactions. Solvent, substrate structure, structure of the nucleophile, concentration of the nucleophile, and nature of the leaving group are the 5 factors which affect this nucleophilic substitution reaction. So let us see each one by one. First is the solvent. Solvent affects rate of both SN1 reaction as well as SN2 reaction. So let us see each one by one. First, let us try to understand the effect on SN1 reaction. As you all know, carbocation is an intermediate in SN1 reaction, and formation of carbocation is the rate determining step. So, carbocation is the product in the first step. Now, if there is polar protic solvent exists in form of dipole like this. Okay, there is a negative part and there is a positive part. So, polar protic solvent molecules orient them around the carbocation in such a way that the carbocation is stabilized. Their negative charge is towards the carbocation, positive charge is away from it. This is something similar to micelle formation that you may have learned. Okay. Now, the net result is carbocation is stabilized by polar protic solvent, and therefore polar protic solvents favor the formation of carbocation and favor the rate of SN1 reaction. Okay. What happens to polar aprotic solvent? Polar aprotic solvents, examples are DMF and DMSO. Now, their structures are such that they can stabilize the cation very effectively. They do not stabilize the anion. Okay, so polar aprotic solvents also favor SN1 reaction, but they also favor SN2 reaction. Let us see how. SN2 reaction is a single step reaction where the nucleophile is involved in the rate determining step. This we have seen in the previous lecture. Anything that stabilizes the nucleophile will reduce the rate of the reaction because nucleophile is not the product, it is the starting material. Okay. Now see here, polar protic solvent can stabilize the nucleophile in a reverse way. See, this is a nucleophile and the positive part of the dipole is oriented towards it. So this stabilizes. Okay. Whereas polar aprotic solvent, as I mentioned, can stabilize the cation very effectively. It does not stabilize the nucleophile. So, polar aprotic solvent favors the SN2 reaction. But non-polar solvents also favor SN2 reaction because they do not stabilize either cation or anion. Okay, they are non-polar, do not exist in form of dipole. But there is a problem. Small nucleophiles like hydroxide ion or cyanide ion are not soluble in non-polar solvents. Alkyl halides are soluble in non-polar solvents. So, how to proceed ahead? There is a way out, and that is phase transfer catalyst. Okay. Alkyl halide, as I mentioned, is soluble in non-polar solvent. The nucleophile is not soluble in non-polar, but it is soluble in aqueous or polar solvent. Now, when you take alkyl halide in non-polar and nucleophile in a polar solvent, they will form a biphasic mixture like chloroform water or benzene water or something like that. As a result, what will happen? The nucleophile remains in the aqueous phase, alkyl halide remains in the non-aqueous phase. So, the contact of the nucleophile and the alkyl halide is not efficient. So, the rate of the reaction is reduced. To address this, a phase transfer catalyst is used. The structure of the phase transfer catalyst consists of a polar part and a non-polar part. The examples are quaternary ammonium salts and crown ethers. Just see this. This is a polar part, and this long alkyl chain is the non-polar part. Similarly, in case of crown ethers, this part is polar, whereas the alkyl chains are the non-polar part. Okay, now how does it function? This is a beaker, suppose. There is a polar aqueous compound, non-polar solvent on the top. Now, a phase transfer catalyst is a molecule that sits at the interface. So, its polar part points to the aqueous solvent and non-polar part points to the non-aqueous solvent. Okay. Look at the structure of quaternary ammonium salt. There is a positive charge with nitrogen, and so along with it is bromide. Now, when this phase transfer catalyst is present at the interface, what happens is bromide, which is present associated with the cation, is exchanged for hydroxide. Okay. Then rapid stirring causes this catalyst to invert itself. Now, how does it look like during stirring? Now, it looks like this. The polar head was pointing in the aqueous region. Now, it tumbles and points in the non-aqueous region. And because of this, OH enters the non-polar phase, reaction occurs. And this is the way a phase transfer catalyst accelerates the rate of the reaction. Okay. There is another phase transfer catalyst, and that is a crown ether. How does it work? OH enters the nonpolar phase by attaching itself to the entrapped cation. This structure entraps a cation. Okay. And associated with the cation is anion. So, the anion is transferred by phase transfer catalyst. Now, second part is the substrate structure. How substrate structure affects the SN1 reaction? It affects the SN1 reaction in two major ways, steric effects and electronic effects. Let us see what are the steric effects. Okay. The spatial arrangement and number and types of atoms attached to the reaction center affect the course of nucleophilic substitution reaction. That is the steric effects in nucleophilic substitution. Let us try to understand how. If the bulkiness of the group increases around the reaction center, what happens? The backside attack of SN2 reaction is not possible. Okay? So, because the approach of the nucleophile is hindered. Therefore, as the bulkiness of the group increases, the rate of SN2 reaction decreases. Look at this. Methyl iodide exclusively undergoes SN2 reaction. Ethyl iodide, just see the rate is decreased. Isopropyl iodide further decreased. And for tertiary butyl iodide, it is practically zero. On the other hand, carbocation is an intermediate in SN1 reaction. Okay, now the transition state has carbocation-like character. And so the reactivity of alkyl halides follows the order of stability of carbocation. That is, tertiary alkyl halides react fastest in SN1 reaction, followed by secondary, followed by primary. Now consider the SN2 reaction. We said that primary alkyl halides undergo preferentially SN2 reaction, but as the size of the group R increases, have a look over here. This is 2 carbon, this is 4 carbon, and this is 6 carbon chain. So the 1 carbon and the 2 carbon containing compound preferentially SN2. The 4 carbon compound also undergoes SN2 mechanism, but a 6 carbon compound preferentially undergoes SN1 reaction. Now, SN1 reaction has carbocation intermediate and it is accompanied by rearrangement, and that is why you see the product is a secondary alcohol. There is another factor that is involved, and that is relief of steric stain. This is observed with SN1 reaction. Okay, you know SN1 reactions have carbocation intermediates. The carbocation has trigonal planar geometry. Okay, the bond angle is 120, whereas the substrate is sp3 hybridized with a bond angle of 107. So, conversion of substrate to carbocation increases the bond angle and relieves steric stain. Okay, so bulkier groups in SN1 reaction accelerate the rate of reaction. Look at this. This is tertiary butyl, and this is one group is tertiary butyl and there are 2 methyl. Here all 3 are methyl. Now when we compare the rates of SN1 reaction of A and B, A reacts 4.4 times faster. Why? Because formation of carbocation relieves the steric stain to a greater extent. Okay. Coming to electronic effects, SN1 reaction, the stabilization of carbocation by neighboring group leads to acceleration of reaction. For example, have a look at this structure. When this forms a carbocation, this carbocation is stabilized by resonance. Just see how the carbocation is stabilized by resonance. Okay. Similarly, a benzyl carbocation or an allyl carbocation is resonance stabilized. This we have seen in the lecture on carbocation. So, when a carbocation is stabilized, SN1 reaction is favored. In SN2 reaction, there is a specific substrate that favors SN2 reaction. Have a look at this. This cannot undergo SN1 reaction because the carbocation formed will be this. Okay. Now, if this is the carbocation formed, there are 2 positive charges adjacent to each other because carbonyl carbon carries a positive charge, partial positive charge. And so such carbocation is going to be highly unstable. So SN1 reaction is out of question. But have a look at SN2 reaction when the nucleophile is approaching from the other side of the X. The nucleophile forms a partial bond with the reaction center carbon, but it can also form a bond with the carbonyl carbon because this is also partially positively charged. Okay. And so such structure, such transition state is highly stable, and such substrates preferentially undergo SN2 pathway. So try to understand this. If we plot the substrate structure versus rate of reaction, the SN2 reaction rate goes on decreasing from primary to secondary to tertiary. Whereas for SN1 reaction, the rate goes on increasing from primary to secondary to tertiary. Okay. So you can see that here is secondary. The secondary alkyl halides don't favor either SN1 reaction or SN2 reaction, and therefore other factors can decide whether secondary alkyl halides are going to follow SN1 course of reaction or SN2 course of reaction. Okay, with this, we end the lecture. I am Dr. Urmila Joshi. If you appreciate this lecture, please hit the like button and subscribe. Thank you so much.